for the average neutral number, do we just find the average number, or what do you mean by average?
Yeah. So that's the average neutral number.
Oh.
Yeah, so there's a such thing as like a local neutral number, but it's really not that useful a lot of the time. So we're gonna use this one. Yeah, so if you look at the notes, it's in there, but you literally never use the local neutral number. So that's the one.
All right, and then if we're off by like, because I think my number's off by like, I think it's 11,000.
Yeah.
I think about 12,000 one of them. Like I
Usually if it's like, if you're off by like 10 or something like that, there's not that big a deal.
it can really affect like other values. So it's like
Yeah.
H coefficient, 43.2.
For this one, I might have,
It's off by a couple, but then the next few were.
yeah, so I think probably what happened in this one, I might have used the neutral correlation for a mixed boundary layer.
I did try that one as well, but then I
Yeah.
got like, for the mixed one, I got like a high number, so I got 12,800.
Okay.
So I did try both.
That shouldn't be that big a deal. You're only about maybe like 10% off or something. I might double check my calculations too. Yeah.
And then also one more question.
Yeah.
Well, this is where I get confused on. It's like the temperature difference. Is it hot first and then the
Yes.
colder one?
Yeah.
All right.
Yeah.
Find that one.
Yeah. Usually you want a positive number for the heat.
Positive?
Yeah.
All right.
You
Yeah.
get high minus one.
That's kind of where I kept getting mixed up.
Mhm.
I think.
Yep.
Which one we got?
What's up?
Oh. Yeah, for.
Yeah, so if you actually check your Google Calendar, it's on there, but I'll send you a record.
Right.
Yeah.
Oh, I think that's where I messed up my. What's that? But I let it. Yeah, what is
Teamwork, right? Oh, yeah. Oh, yeah. Dr. Tran, how are you, sir?
Good, how are you?
Good. Good.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. We're end of week 9, so we have one more week of class next week and then spring break. So I think we're all hopefully looking forward to spring break. Okay, so plan for today is we're going to finish up our lecture notes on internal convection. So So there's just some more to do for that. I have a couple examples to do. And then we'll be ready to talk about heat exchangers next week. All right, so some announcements. Member homework for that's due tomorrow, I believe. So make sure you guys are working on that. If you have questions, I do have office hours right after the lecture today. Or you can always email me your questions as well. Typically, just because I know, middle of the day, I know sometimes it can be hard to make the office hours that, if you have questions, just email your work to me and then, we can kind of work through it there. So I should be available most of tomorrow. I am busy typically in the mornings on Fridays, but tomorrow afternoon I can answer emails pretty quickly. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go and get started. Okay. So on Tuesday, we started talking about internal flow convection. So kind of the theme of this entire unit here is, looking at convection in various different scenarios, right? Because one thing that we've been kind of talking about for the past couple of weeks is that the flow conditions or the fluid mechanics of the situation, they play a big impact in terms of the heat transfer in these kinds of situations. So every time you have a different type of geometry, a different type of flow condition, that's going to necessitate kind of a different discussion on the convection, okay? In particular, in internal convection, we're looking at flow situations where the flow is bound on all sides by some kind of solid surface. Okay, so kind of the very typical case of internal flow convection is we have flow in a pipe. Okay. So you have flow coming in here, right? So kind of the big thing with internal flow convection is that there's no sense or there's no notion of a free stream. Because once the flow kind of enters this internal system, right, the boundary layers from all of the lateral walls are eventually going to meet. Okay. And so eventually, for pretty much every internal flow, unless your pipe is only, a couple millimeters long, you're going to have a region which we call the fully developed region. Right? Right. And so the characteristics of the fluid flow, the characteristics of the heat transfer in this fully developed region have a very different character, very different behavior from what we've discussed from the free stream, which is what we did last week. Okay. In particular, the one of the main differences is, because we have flow that's bounded on all sides, right? Right. What we typically say is that inside this pipe, we have a finite amount of fluid. Okay. And so oftentimes you can compute, there's actually, a number you can compute for the volume of fluid inside a pipe. You just take the volume of the pipe itself, right? And that's significant because as we apply heating, right? So let's say that we're heating the fluid from externally, or let's say that, the fluid is losing heat, right? Either case, right? Because we have such a small amount of fluid inside this pipe, any kind of heating or cooling that we apply to the fluid is actually going to make a big impact. It's actually going to influence the temperature of the fluid itself. Okay, so that's kind of the biggest difference, I think, compared to pretty much everything we've heard so far, is that the temperature of the fluid inside the pipe is actually going to change along the length of the pipe. That's in very kind of stark contrast to external flow, where we assume that, our free stream temperature, our free stream velocity, those, usually those are not really affected by the fluid. And so we kept those constant, right? But in internal flow, we have, instead of T infinity, right, we have Tm instead, which is the mean temperature, right? And we know the mean temperature is actually going to change, okay? Right, and so that's the first thing that I want to kind of start with today is, what are some methods, or how do we actually solve for this mean temperature, and how does it typically change from one point to another along the pipe? Okay. So let's see if we can come up with an equation or formula, or just kind of a way to get a sense to compute this mean temperature at two different points in our fluid, okay? Okay, so let me do this one more time. Let me go ahead and draw our pipe here, okay? We have flow coming in. And let's say that, typically we describe the flow as a velocity, but since our velocity is also changing, across the cross section, it's a little bit more convenient to talk about it in terms of its mass flow rate, okay? So I'm going to start to introduce m dot. So m dot here is the mass flow rate of fluid going through the pipe. And so typical units for mass flow rate, you've probably seen it in other classes before, but it's going to be a mass per second. So that tells you just how much mass of fluid is going through the pipe, at any given second. Okay. Okay. So the next thing I'm going to draw here is I'm going to draw an energy balance. Okay. So let's draw kind of a very small control volume here. So this little kind of dotted box here, this is our control volume, right? And on this control volume, we're going to do an energy balance. Right? And so we're basically going to use that energy balance as a way to compute, or at least come up with an expression for the mean temperature in the fluid itself, okay? Okay, so one thing we do need to know is that the length of this control volume here is going to be dx, okay? I've kind of blown it up here, but you can assume that this control volume is very small, but it at least does span the entire cross section of the pipe itself, okay? All right, so to kind of keep things simple, we're just going to assume one source of heating. And so we're going to say that we're going to have some heating coming from the wall into this control volume, okay? And that's going to be Q, we'll call it Q convection, okay? So Q convection, or I guess to be more specific, it's dQ convection, okay? Just to indicate that it's on a small control volume. Okay? So dQ convection, right? This is going to be the heating that occurs through the wall into our control volume. Okay. So let's see if we can come up with an expression for dQ here, based on some things that we know. Okay. All right. So first thing we're going to set it equal to is we're going to say set dQ convection equal to our Newton's law of cooling. Right. So anytime we have convection heat transfer, we can always relate that to our Newton's law of cooling. Okay? So first thing we can do is we can say that dQ convection is equal to H, the convection coefficient, multiplied by the surface area of this segment here. Okay. So I'll call that dA for now. So this dA is going to be the surface area of our control volume. And then as part of Newton's law of cooling, we need to multiply this by a temperature difference. And in this case, the temperature difference is going to be the difference between the surface temperature of the pipe and the mean temperature of the fluid. So this is going to be Ts minus Tm. Okay. All right, where Ts, let me kind of label it in the figure here. Ts is going to be the surface temperature at the wall, and Tm is going to be the mean temperature kind of within that control volume. Okay. And because we've picked our control volume to be relatively small, this mean temperature we're going to assume is kind of consistent throughout the entire volume of our control volume. Okay. Yeah.
The whole inner wall is all uniform temperature.
Yes, we're going to assume that for now, or at least for this section that we're considering. Yeah, we're kind of taking advantage of the fact that our control volume is small to make those constant. Yes, questions? Oh yeah. Mm-hmm. Yeah, so you know, in kind of a generic case, both the surface temperature and the mean temperature of the fluid, that is going to evolve, you know, from one point to the next. And so if we look at another control volume here, right? The surface temperature and the mean temperature are going to be different at that location, but we're just focusing on just this small one, kind of right at the middle there. Okay. One other thing that I'm going to do just to kind of simplify this a bit, we can come up with an expression for the surface area here, or we can kind of plug in for that a little bit, right? Because we know the width of this control volume, we know is dx, right? So to compute this, the surface area of this section, and we kind of leverage the fact that this is a cylindrical geometry, right? We know that the surface area is going to be equal to the product of the perimeter of the pipe, so around that cross section, multiplied by the width of our section, so it's going to be P dx. Okay. I should probably stop using red. And so if we plug that in, we get dq convection is equal to HP dx times Ts minus T infinity. Okay. And this right here is just simply an expression of Newton's law of cooling on this kind of small control volume. Okay. All right, any questions on this so far? Okay. All right, so let's see if we can come up with another expression for dq convection, because I did say that we are going to do an energy balance on this control volume. Okay, so let's do that. So let's do our energy balance now. Okay. Oh, thank you. I messed that up. So it shouldn't be T infinity, it should be Tm. Thank you. Okay, so for our energy balance here, you know, we're basically going to say that the heating that we're applying to this control volume is going to result in a change in temperature. Right? Because the conservation of energy, you know, energy can't be created or destroyed. And so if we are inserting energy into our system, into our fluid, that has to have some kind of effect that we can observe. And kind of the first thing that we can observe when you add thermal energy is a change in temperature. Okay. So what we can say is that dq convection, right, is equal to a change in temperature. So we can say this is equal to dTm, right? So this dTm here, this represents a change in temperature in the fluid. Okay. And then we need to multiply by some other factors here just to mostly to make the units work out, but also just to account for the fact that different fluids are going to have different changes in temperature, right? Because we know that different materials or different fluids have different heat capacities. And so that should be reflected here in this equation as well, right? And so kind of the two things we need to multiply this by is first of which is CP. CP is the thermal capacity of the fluid. So remember, we saw this quantity back when we did lump capacitance. Okay. So CP is a material property of the fluid, just like its thermal conductivity. So different fluids are going to have more capacity than others. Okay. And then we're also going to multiply this by the mass flow rate of the fluid itself. Okay. All right. So m dot is simply just the mass flow rate of the fluid that we kind of went over earlier. Okay. So this expression here represents a change in temperature that results from the heating that's applied, right? So the heating that's applied is equal to the change in temperature multiplied by the thermal capacity and the mass flow rate, okay? Okay, so this is essentially kind of what we get, but just by doing a simple kind of conservation of energy, okay? And now if you look at these two expressions that we have, so we have our Newton's law of cooling expression up here, and we have our conservation of energy equation here, right? These are two expressions that we have for dq convection, right? Or in other words, two different ways to kind of express the same thing. So what we can do is we can then take these two and set them equal, right? Because they're equal to the same thing, right? And then that's going to give us an equation that we can use to solve for the mean temperature, okay? Okay, so let's see what happens when we do that. So when we do that, we get, let's do the Newton's law of cooling side first. We have HP dx multiplied by TS minus TM. And this is equal to, so that's the Newton's law of cooling side. We are now going to set this equal to the conservation of energy side. It says dTm multiplied by CPm dot, okay? Okay. So let's rearrange the terms a little bit here, just to kind of, just so that we can obtain a differential equation for this. So I'm going to take dx. I'm going to divide both sides by dx. Okay. So that's going to come over here. I'm going to take this CP times m dot, and I'm going to divide both sides by that. And so that's going to end up on that side. Okay. And so if we do that, we get, let's see, P times H divided by m dot CP times the temperature difference TS minus TM is equal to dTm dx. Okay. All right, and so what we have here is we have an equation that we can use that describes the evolution of the mean temperature in an internal convection situation. Okay. All right, any questions on how we got this equation, here? Okay. So looks like a fairly straightforward equation. So, it's a differential equation. So we do have a first order derivative, but we've definitely seen scarier in this class. But turns out this equation here is actually very difficult to solve, because you can't really just straight up integrate it, right? Because first of all, you have Tm on this side, right? That's what we're solving for. We have Tm on this side as well, right? And so just by the existence of these two things on both sides, this tells us that Tm changes along the length of the pipe. Or in other words, we can say it changes in the x direction. Okay. And so that's kind of the first thing that complicates this. And so it's not just going to be a straight up integral on both sides. Okay. But another thing that we haven't really talked about as well is that another thing that can change along the length of the pipe is the surface temperature. Okay. And we don't really have an equation that will tell us how TS will evolve. So this equation, even though it looks quite simple, and in fact, everything out here, the pH, m dot Cp, typically, even though those are even typically constants, the fact that we essentially have two unknowns in this equation, both Tm and Ts, means that, we cannot really solve this equation without applying some assumptions. Okay. So we can really only solve this equation under some very specific circumstances, very specific assumptions, which, in reality, so the two assumptions that we're going to make here, the two conditions, it's very hard to find one case or the other in reality. We'll talk about some cases where these assumptions are valid, but most practical situations are never going to be one or the other. They're going to be kind of more in between. So, part of the challenge of doing these problems is kind of making the judgment call or making kind of your own judgment in terms of which of these situations is going to be closer to. Okay. Okay. Okay, so what are these two assumptions? So what are these two cases that we're going to look at? So the first situation, which is the one that's a little bit simpler, is if we assume that we have constant heat flux from the wall. Okay. So that's the first example that we'll do, and you'll see what the solution looks like in that case. Okay. And the second condition, which is a more appropriate in other situations, is if we assume that our surface temperature, so the temperature at the surface of the pipe, we assume that is going to be constant. So you're never going to have both of these, and so you're going to have just one or the other. So, I kind of want to emphasize that. So for this situation, you're going to choose one of these assumptions. And which one you choose is going to be more appropriate in some situations than others. Okay. Okay. Any questions on this so far? Okay. All right. So let's look at the case for constant heat flux from the wall. Okay. So what this is basically saying is that as we go along the pipe, right, the heat flux that's coming in okay, so the heat flux we're going to say is like QS double prime. Okay. So the heat flux in the pipe is going to be the same from one location to the next. And so we have a constant kind of QS double prime. So QS double prime is going to be the same at the end of the pipe. It's going to be the same at the middle of the pipe. It's going to be the same at the beginning of the pipe. Okay. So all throughout the pipe, you have a constant kind of influx of heat, and that value is consistent along the entire length of the pipe itself. Okay. Okay. So a common situation where this would occur is that maybe you have some kind of consistent heating, maybe applied by some electric heater. So you know it's common nowadays to have some kind of maybe electric heater that's wrapped around the pipe, that's supplying basically a constant heat flux throughout the entire length, right? Another case, actually, you know, just thinking about it. So if you look at the design of newer houses nowadays, it's very popular to have something called a tankless water heater. So the way a tankless water heater works is that, you know, it runs the water main pipe kind of through this tankless water heater, right? So there's usually a section of pipe that kind of goes through your tankless water heater like this, okay? And then on this pipe, you basically have a, you know, if you talk to a plumber, if you talk to a person, they say that you basically have like a jet engine inside your water heater. So you have basically just a ton of flames, right? You have basically like a broiler that's heating your pipe through this section. And so the idea is that, you know, you don't, without a tank, without a water tank, or without a heat tank, you know, this device is able to provide enough heat through this pipe to provide enough hot water for your entire house. And so, you know, this would be another example if you have a constant heat flux through the pipe, because this flame is kind of consistent throughout the length of that pipe. It's really cool. I was able to kind of take a look at mine about a year ago when it broke, and I was bugging the plumber to let me see. But yeah, it is kind of a cool kind of thing. Okay. So in this situation with a constant heat flux, this actually simplifies our calculations quite a bit, right? Because if QS double prime is constant, what's another expression for QS double prime? Well, we can put this in terms of our Newton's law of cooling, right? And so we can say this is equal to H times TS minus TM. Okay. Right, that's just the definition of heat flux in internal convection. It's the convection coefficient multiplied by the difference in temperature. Okay. But if these two are constant, right? And so if we kind of just make this jump in logic that, you know, QS double prime is constant, that means this quantity H times TS minus TM is also going to be constant. Now, TS and TM individually might be changing, but their difference is always going to be constant in this case. Okay. So we can actually kind of make that substitution. So if we come back to our differential equation up here, so actually let me write it down again. We have dTm dx is equal to pH over m dot Cp times Ts minus Tm. Okay. So this right here, this is our generic formula for the evolution of mean temperature in internal flow. So we haven't made any assumptions just yet, but if we make the assumption that this quantity here, this H times Ts minus Tm, if we assume that this is constant, right? Then we can kind of substitute in for that. And so if we assume that it's constant and we plug in Qs double prime for that, we have dTm dx is equal to P over m dot Cp times Qs double prime. Okay. Suddenly, we have a very easy differential equation to solve right here, because everything on the right-hand side of this equation, the perimeter of the pipe, well, if we assume that the pipe is constant surface area, which most pipes are, unless you're designing a literal jet engine, and then we assume the mass flow rate, the heat capacity of the fluid, and of course, Qs double prime, the heat flux is also constant, okay? So that means now everything on this side of the equation is constant. So that's fantastic, because then what we can do is we can integrate this with respect to x. And then what we get from that is Tm of x is equal to, we have integral of PQS double prime divided by m dot Cp, all that's constant. And so we just end up with PQS double prime divided by m dot Cp times x. Okay. And then we have to add our arbitrary constant. But in this case, our arbitrary constant will usually be the initial condition or the boundary condition for the mean temperature. Right. And so this Tm0 here, this is going to be the mean temperature of the fluid, usually at the entrance of the pipe, or usually at a place where we know the mean temperature is. So this equation right here that I've boxed, this is the evolution of mean temperature in the case where we have constant heat flux through the wall.
At the entrance of the pipe or the entrance of the control volume?
Entrance of the pipe. Yeah. It doesn't necessarily have to be the entrance of the pipe, just at a location where you know the mean temperature. Yeah. Okay, and I want to emphasize that last part. So this equation here is only valid for cases when you have constant heat flux through the wall. Okay. So how do you know when you have constant heat flux through the wall? Well, you know, for this class, the problem will tell you if you have constant heat flux or not through the wall. But you know, as you kind of do more examples of this, and as you kind of see some more examples out in the wild, like for example, you know, this tankless water heater, you know, you'll start to get a sense of kind of which cases it's where it's more appropriate to apply this assumption here. Okay. Okay, so let's do a quick example of this, just so you can kind of see how all of this kind of works together. Okay, so let's look at a tankless water heater. Okay. So let's say a tankless water heater is responsible for heating the water that goes through it from 20 degrees C to 60 degrees C. Okay, and the way it's going to achieve this is that it's going to be inputting a constant heat flux through the wall. All right, and so actually we do know that number. So let's say that our heat flux, QS double prime is equal to 1.5 times 10 to the fourth watts per meter square. Okay, so our figure for this is going to look like the following. Okay, so we have our pipe. We know the pipe is going to have a constant heat flux through the wall. Okay. So coming through the wall here, we have QS double prime. That's going to be heating it. We actually know the value of QS double prime in this case. Okay. Other information that we know is we know the mean temperature at the inlet. And so we can say that Tm at the inlet of the pipe, right? So when the water comes in, it's going to start at 20 degrees Celsius. Okay. And by the time it reaches the end, right? And so if we mark out Tm at the outlet or TMO, this is going to be 60 degrees Celsius. Okay. So the water is going to heat up from 20 degrees to 60 degrees. Okay. Other information that we know is we know the diameter of the pipe. So the diameter of the pipe, and we've kind of already assumed that the pipe is cylindrical. The diameter of the pipe is going to be 20 millimeters. Okay. Let's see, what else do we know? We know the mass flow rate. We need to know that. Okay. So the water is going through the pipe at a mass flow rate of 0.1 kilograms per second. Okay. And we also know the surface temperature of the pipe as well. So the temperature of the pipe, at least at the outlet, I should specify that. So the temperature of the surface at the outlet this is equal to 70 degrees Celsius. Okay. Okay. So with all this information here, let's compute two things. Exactly. Yeah. So that's the first thing we're going to compute is we need to compute the length of pipe that's needed to achieve these conditions. Okay. And number two, based on the conditions at the outlet. So at the outlet, we actually know the surface temperature and the mean temperature. Let's use that information to compute the convection coefficient of this flow. We don't really need the convection coefficient that you're going to see. So we're going to actually do most of the analysis without the convection coefficient. But it's at least convenient to know. It's kind of nice to know what it is for this case. Okay. So this problem here, this is mostly a problem that has to do with our mean temperature formula. And so we're going to use that first to compute the length of the pipe. Okay. Any questions on just the setup for the problem, any of the parameters that we have here? Okay, all right, so let's get to solving it. So let's compute the length of pipe needed. Okay. So to compute the length of pipe that's needed, we are going to need to use our mean temperature equation. So our mean temperature equation Tm of x is equal to, and so we're going to use the version of this equation that's for constant heat flux, right? So that's the one we kind of developed right before we started this example. So it's going to be P QS double prime divided by m dot Cp times x plus Tm of 0. Okay. Okay, so we can plug everything into this equation here, and eventually what we're going to solve for is we're going to solve for x, right? Okay. Because for TMO right here, Tm, or I should say Tm of 0, this is essentially our mean temperature at the inlet. Okay, which we know in this problem is 20 degrees C. Right. We want to find out how long it's going to take in order to heat up the fluid from 20 degrees to 60 degrees. And so this Tm of x, we're going to set this equal to Tm at the outlet, which is 60 degrees C. Okay. Okay. So besides that, we know QS double prime. This was given to us in the problem. And so this is 1.5 times 10 to the 4th watts per meter square. Okay. We know m dot. M dot was also given to us in the problem, the mass flow rate. This is 0.1 kilograms per second. Okay. The perimeter wasn't directly given to us, but we were given the diameter. And so the perimeter is just going to be pi times the diameter. Okay. Make sure to convert that diameter to meters. So the only thing that's missing here is the heat capacity of the fluid, or heat capacity of water in this case. Okay. So that wasn't given to us in the problem, but this is something that we can look up because this is basically a property of the fluid. Okay. Right, so you can use one of the tables in the textbook, or you can use the online fluid calculator that I sent out end of last week. Okay. Then of course the question is, what temperature do you use, right? Because you need to specify a temperature when you're applying these properties. Well, we know our fluid here is going to transition from 20 degrees Celsius to 60 degrees, and so right in the middle is about 40 degrees Celsius, right? So it's not going to be perfect because the heat capacity is actually going to change as the fluid transitions from 20 degrees Celsius to 60 degrees Celsius, but it's a good average point, okay? So at 40 degrees Celsius, then what we have is Cp is equal to 4,179 joules per kilogram Kelvin. Okay. All right, so if we plug all those numbers in, then what we get is 60 is equal to 2.255 times x plus 20. Yep.
So that 40 degrees Celsius, is that related to the film temperature at all?
It is. So it plays the same role as the film temperature because you do need a temperature to evaluate these properties at. It's just that we're using a little bit of a different definition here. And so we're computing the mean, or the average of the mean temperatures here. So the average between the inlet and the outlet temperature.
Which is film.
Well, film temperature, I guess specifically, that's the temperature within the boundary layer. But in internal flow, we don't really have a boundary layer. So it's
Oh, okay.
Yeah.
So I'm thinking external flow.
exactly, yeah. But it plays the exact same role. So it's the temperature you're going to evaluate the properties at. It's just here we have a slightly different slightly different definition for it. Yeah. Mhm. Okay. So this is our equation here. So the last thing we need to solve for is x, which is going to be the length of the pipe. Okay. And so if we solve for x, what we get is x is equal to 17.74 meters. Okay, so that's a pretty long pipe, but also heating water from 20 degrees Celsius to 60 degrees is also a lot of heating too. So it makes sense that the length of the pipe is quite long. Okay, so that's part one of the problem. Part two is to compute the convection coefficient. Which, again, we didn't really need the convection coefficient here. We already kind of learned our design variable, the length of the pipe without it. But it's good trivia, right? Okay, so at the outlet, and what you're going to see here is that, we actually have all the information we need. We actually don't need to use the Nusselt number here at all. Okay, so at the outlet, we know the mean temperature is 60 degrees Celsius, and we know the surface temperature is 70 degrees Celsius, right? So both of those pieces of information were given to us in the problem, right? So we know the difference between the surface temperature and the mean temperature. And we also know the heat flux, because we know the heat flux is consistent throughout the entire pipe here. So the heat flux here is 1.5 times 10 to the fourth watts per meter square. Okay. So actually, based on all this information, we can compute H kind of straight up from this situation. Okay. Because if we apply Newton's law of cooling, our favorite formula, right? We know that QS double prime is equal to H times TS minus TM, right? We know every quantity here. And so we can just compute H is simply equal to QS double prime divided by TS minus TM, right? And so we just do that simple division there. We get 1,500 watts per meter square Kelvin. Okay. So this kind of highlights an important point that I kind of want to highlight here, that sometimes you don't need to go through the entire kind of, song and dance of computing the Nusselt number to get the convection coefficient. Sometimes you can extract that information for internal flow just straight off the property or straight off the numbers from the problem. So you have to kind of be careful of these situations. So you're actually going to see, we're actually going to revisit this later. So, we're not done with the Nusselt numbers. We are going to bring them back. And so when you have a choice to compute the convection coefficient, either using a Nusselt correlation or using, information from the information from the problem, this method is going to be more accurate. And so the Nusselt numbers should kind of only be used in kind of a last kind of a last ditch effort. And you're gonna kind of see why very soon, probably at the end of class. Okay. All right, any questions on this so far? Okay, all right, so let's look at the other case. So let's look at the case. So this was the first assumption that we can make. So this was the assumption of constant heat flux through the wall. So let's look at a case where we have constant surface temperature instead. Okay, so let's start by writing out our mean temperature evolution equation. So we have dTm dx is equal to H times P divided by m dot Cp times Ts minus Tm. Okay. Right, so that's our generic evolution equation. And so in this case, we're going to assume that Ts is constant. So this kind of illustrates a situation where if you have a pipe that looks like this, right? If we measure the surface temperature of the pipe, so if we measure the surface temperature here, and the surface temperature here, and the surface temperature here, right? So what it means to have a constant surface temperature means that the solid part or the surface temperature of the pipe is going to be constant throughout the entire pipe, okay? And we'll do an example to kind of show you what that looks like in a bit. Okay. So this simplifies our equation because now that we know that Ts here is constant, I drew two arrows that said the same thing. Well, it's super constant now, right? Now we only have one more unknown in this equation, and that unknown is Tm, okay? So let's kind of refactor this equation to solve for it, okay? So to make things a little bit easier to solve, I'm going to bring back an old friend. So let's bring back our excess temperature. Okay. So remember, excess temperature is the difference in temperature between two things. And so in this case, we're going to take the difference of Tm minus Ts. Okay. Right. Since we know that Ts is constant, that means if we take the derivative of the excess temperature, d theta dx, that means since Ts is constant, then this is just be equal to Tm dTm dx. Okay. Okay, so if we plug that back into our evolution equation up here, we get d theta dx is equal to minus p h, or I should say, I should keep it consistent, hp divided by m dot cp multiplied by theta. Okay. We have that minus sign out in front on the right-hand side because of how theta is defined here. So theta is Tm minus Ts. If we look back at our equation here, we have Ts minus Tm. So we need a minus sign to kind of make everything kind of work out, okay? All right, so here we have a first order equation, but it is one that we can solve pretty easily using separation of variables. Okay. So let's go ahead and do that. So let's take theta and let's go ahead and put it in the denominator on the other side. You have d theta over theta is equal to minus hp over m dot cp dx. Okay. Let's go ahead and integrate both sides. And so if we integrate both sides, we get the natural logarithm of theta is equal to minus hp divided by m dot cp times x plus c. Okay. And so if we want to simplify this and solve for theta, we're going to raise both sides to the e. Okay. And so on the left-hand side, that's going to give us theta of x is equal to e raised to the minus hp over m dot cp times x. Okay. Then just like we did previously, when we solve these equations, we have this multiplied by e to the c, right? Because when you put two things in an exponent that are added together, you're just multiplying by their by them. And so just to make things a little bit simpler, I'm going to put the constant out in front. Okay. Just like that. And unlike previously, unlike back when we did our lump capacitance, I'm actually going to plug back in Tm. So let's plug back into our excess temperature. Okay. And so our excess temperature is Tm of x minus Ts. Okay. That theta naught there, that theta naught is a constant that defines kind of the excess temperature at the inlet. And so that theta naught there is going to be Tm of 0 minus Ts. Okay. Multiplied by e to the minus hp over m dot cp times x. Okay. All right, and then last thing I'm going to do just to simplify this whole thing, I'm going to move the surface temperature and move it over to the right-hand side. So we get just one kind of clean expression for Tm. Okay. And so we get Tm of x is equal to quantity Tm of 0 minus Ts multiplied by e to the minus hp over m dot cp times x plus Ts. Okay, so this is our evolution of mean temperature when the surface temperature is constant. Okay. Any questions on how we got this expression here? Okay, so we have two solutions basically. So we have one solution for Tm when the wall flux is constant, another solution for Tm when the surface temperature is constant. And so, when you're doing in these internal convection problems, that's one thing you have to determine, which is more likely to be the case. Is it more likely that our surface temperature is constant, or is it more likely that our wall flux is constant as well? Okay. So for each problem, so when you're doing these problems, you'll see these problems in homework 5 that I'm going to post next week. You have to decide whether it's a constant heat flux type situation or a constant surface temperature type situation. Okay. Sometimes the problem will just tell you, so you don't have to decide. But if the problem doesn't tell you, then you have to kind of make an assumption one way or the other. Okay. Now, before we do an example with this, that's probably going to be the last example that we do. Let's talk about Nusselt numbers because we haven't really talked about those quite yet. And the reason I'm kind of taking a break here to talk about the Nusselt numbers is that if you look at our result, and so if you look at our solution here for the mean temperature in the case of constant surface temperature, you can see that we have H in this exponent here. It's a little bit small, so it's a little bit easy to miss. But we actually need to know information about H to complete this mean temperature equation here, okay? And so when you're doing convection problems with constant surface temperature, oftentimes you're going to be stuck because you need to determine H before you can kind of move forward, right? And usually the best way to determine H in these situations is to use the Nusselt number, just like we did with the external flow, okay? Okay. So Nusselt numbers for this for internal flow. Now, this is a very interesting case because if you remember what we talked about at the end of class last time is that once you're in the fully developed region, once you're in that region and it honestly doesn't take long to get into the fully developed region, right? One thing we talked about at the end of class last time was that the shape of the temperature profile across a cross section does not change. Okay. Now, the values of the temperature may change. The mean temperature obviously is going to change. The surface temperature might change if you have a case of constant heat flux, but the shape of that profile is not going to change. It's going to be the same quadratic shape basically in every cross section. Okay. Now, of course, this is assuming laminar flow. That's kind of an important caveat. Okay. And this kind of had one very important consequence, right? Because one thing that our convection coefficient depends on, our convection coefficient depends on the shape of that temperature profile. Right? So depending on how that temperature changes from the surface to the mean, right? That's our convection coefficient depends very strongly on that. Okay. And so this is actually very interesting because so even though the mean temperature is changing, even though the surface temperature is changing a lot of the time, the shape of that profile is not changing. And so if the shape of that profile is not changing, it still has a quadratic shape in every situation. This means our convection coefficient is actually going to be constant. Right? And if our convection coefficient is constant, that means our Nusselt numbers are also going to be constant. And so we have actually a very interesting scenario here where, for internal flows, now granted, you assuming that your flow is laminar, your Nusselt numbers are these kind of magic number type of things, okay? And there's two situations here. So if we look at first a situation with constant heat flux. Okay. Our Nusselt number in this case, so Nusselt number based on the diameter of the flow or diameter of the pipe is equal to 4.36. Okay. And that's equal to the convection coefficient multiplied by the diameter divided by the thermal conductivity of the fluid. Okay. So it is actually equal to just a magic number, which is really interesting because this almost never happens in math and science at all. Okay. We have another expression for the Nusselt number for the case of constant surface temperature. Okay. And so in this case, the Nusselt number based on the diameter of the pipe is equal to 3.66. And that's equal to H times D divided by KF. Okay. Okay. So actually, if you need the convection coefficient in internal flow, it's actually quite simple. And you don't have to kind of go through that whole song and dance because we have these kind of magic numbers here. Okay, so let's take this kind of magic information and let's see if we can compute or recompute our convection coefficient from the previous example. Right, so our previous example was the tankless water heater that we kind of just finished talking about, right? And so part 2 of that problem asked us to compute the convection coefficient based on the heat flux, right? And so from the previous example, we got a convection coefficient equal to 1500 watts per meter square Kelvin, okay? So this was based just purely on the heat flux as well as the surface temperature and the mean temperature. Right, so remember, we didn't use any Nusselt correlations to compute that. So let's see if we can compute our Nusselt correlation using, or let's see if we can compute the same convection coefficient using the Nusselt number that we have up here. Okay. So let's go ahead and plug in for that. So for a situation where we have constant heat flux, our Nusselt number is equal to 4.36, right? And this, of course, is equal to the convection coefficient multiplied by the diameter divided by the thermal conductivity of the fluid, okay? Okay, so let's rearrange this quickly because we know the diameter from the problem. So the diameter given to us in the problem at the time was 20 millimeters, okay, which is equal to 0.02 meters, okay. The thermal conductivity of the fluid, remember, we're evaluating this at the average mean temperature. So this is at 40 degrees C. This is equal to 630 times 10 to the minus 3 watts per meter Kelvin, okay. So we have everything we need here to solve for H. And so if we solve for H, we get H is equal to 4.36 multiplied by KF divided by the diameter. Okay. So we plug everything in, and what we get is 137.34 watts per meter square Kelvin. So that was really easy, right? And so, all we had to really do was just, plug in the diameter from the problem. We had to look up one fluid property. And since we know the Nusselt number was 4.36 in this scenario, we just had to kind of just work through the outer from there. Okay. But you're probably thinking, wait a minute, right? So from this method, we got H is equal to 137, 100, let's round up. We'll say it's 140. Okay. From the problem, we got H is equal to 1500. So these numbers are very different from each other. And so, what gives? So why are we off by a factor of 10 between these two, right? Remember the caveat that I gave, right? So these two Nusselt correlations, this Nusselt is equal to 4.36 and Nusselt number is equal to 3.66. This is only valid in laminar flow. Okay. So that's really important. So in laminar flow, for internal flows, our Reynolds number, remember, has to be less than 2,300. Okay. Which is very limiting. And so probably what's going on in this problem is that because we obtained a much higher convection coefficient, that means our flow is most likely turbulent. All right, so which one's correct? So which one do you use? Well, in this situation where you're most likely going to have turbulent flow, the Nusselt correlation is most likely going to be incorrect, right? Because this is only valid in laminar flow. So in this situation, I would trust this one more, okay? Now, granted, we did have to make some assumptions with this number too. We had to assume that the wall flux is constant. It may not be exactly the case that is, but I would say the real convection coefficient is going to be closer to this one than this one. Okay, so it's going to be probably in the ballpark of 1,200, 1,300, more so than less than 200. Okay. Okay, so if you have turbulent flow, these Nusselt correlations are a little bit off. We'll talk next time on Tuesday what to do if you do have turbulent flow. There is a Nusselt correlation for that. Although spoilers, it's just the same Nusselt correlation we use for external turbulent flow. So that kind of gives you a better approximation than this one. Okay. All right. Any final question before we wrap it up for today? Yeah.
So Reynolds to be less than 2,000?
2,300. Yeah. That's the threshold for turbulence and internal flow. Okay. All right. So that's all we got time for today. And so when we come back on Tuesday, I do have one more example for a constant surface temperature. So we'll start with that. We'll talk about turbulence a bit more, and then we will move on to heat exchangers. All right, so thank you guys for coming this week. Hope you guys have a good weekend, and I will see you guys next week. Yep. Yep.
And I got when we did that, we integrated with data on this side and then with respect to X on.
Exactly. Yeah, we did separation of variables. So at this point right here, we can see that since everything here is a constant, the H, the P, the M dot CP, then we can move X, dx to this side, and then since we have d theta here, we move the theta down here. We integrate this with respect to theta. That gives us natural logarithm of theta, and then on the right hand side we have all of this times X. Yeah. Yes, it's mid-April. So so I don't think the school has released the exact registration. I think it actually comes out tomorrow. When you can register, but then the actual registration dates will be middle of April, April 14th, 15th, 16th.